As we said at the outset of this lesson, our goal eventually is to be able to calculate the shear stresses and normal stresses that occur within a beam when you bend it. The first part of this lesson was devoted to being able to calculate moments of area, which are going to be crucial for allowing us to calculate these shear and normal stresses. The second thing we need to be able to do before we can start talking about stresses is to be able to properly calculate both the shear force and the bending moments that occur within a beam. And so to start, we're gonna consider what should be familiar territory to you, which is the transverse loading of a beam. And so what that means is you have a beam that's horizontal, and say a gravitational field. And we're going to apply a force perpendicular to this. So it could be a concentrated force, a distributed force, and that force could be either uniformly distributed, or it can be distributed with some function along the x-axis. And so our goal here is to be able to determine the bending moment or bending couple and the shear force within this beam, and both of those quantities can vary along the x-axis here. And so there's going to always be two questions that should be at the beginning of evaluating these transverse beam loading problems. The first is, how is the structure loaded? So take, for instance, this given beam, in which we have a uniformly distributed load and we'll have that load be W. So from A to B, which is along some length L, this beam has a uniformly distributed load. As we get more into this topic, we're going to be able to see combinations of load where parts of the beam can be experiencing a uniform load, parts can be experiencing a point load. But we're going to start simple for now. That's the first thing we need to consider. How is the beam loaded? The second thing we need to consider is, how is the beam supported? So here's an example of a beam that's simply supported at its edges. And that means when this thing gets pushed down, it's going to just simply bend into a U. There's going to be no moment applied to those edges. We're going to see different types of boundary conditions where we consider, say, clamped beams or cantilever beams or overhanging beams. And we're going to see how these all contribute to the shear and moments along the edge of a beam. Before we get into it, there's one thing I want to note, and that is about sign convention. So if you have a given element of beam with some arbitrary load, maybe that varies along the x-axis, as you would expect, we're going to call, if that load is pointing in the vertical direction, this would be considered a positive load. So, and we're going to distribute load with a W. If we arbitrarily cut this beam, and so here's the cut, and here's the clean side, and our shear force looks like this. This is what's known as a positive shear force. Both of these are causing the same rotation here, so this is going to cause it to rotate counterclockwise in both cases. And the same thing is true if we arbitrarily cut the beam. And I'll draw it the same way over here. And so in this case, if we have a rotation going that way or a rotation going that way, both of these will give a moment or a bending couple, and we'll call this that positive couple direction. So we can go back to this problem here, where we have a uniformly distributed load along the length of a beam from points A to B. This thing is simply supported. And so the first thing we want to do is get a free body diagram on this structure. So we'll arbitrarily make a cut at some point C, and then we can draw the free body of that point C. So here's this little element from A to C. And in this case, we can re-describe our uniformly distributed load as a point load, W, that's occurring at a distance x over 2, if we call this distance that we're looking at a distance x. So we have a force pushing up at the boundary, and this force pushing up at the boundary we can write as a WL over 2. So it's basically the force times the length, and because there are two simply supporting boundaries, each reaction force is taking on half of this distributed force. We're pushing down here, which means that there's going to be a shear force, V, where we made our cut. And this thing is going to bend, which means we expect there to be a moment, M, going that way. And so, just like a traditional statics treatment, we have our free body diagram. We can sum the forces in the y direction and sum our moments about point C to get our equilibrium equations. And so let's go ahead and do that. So if we sum our forces about y equal to 0, we're going to find that this first force here, the reaction at A, is going to be positive. So we'll have WL over 2. There's going to be a negative force, W. This is W times whatever distance it is, x, which will be coming down. So negative W x. And as you'll note, our shear force here is actually going negative along the cut here, so this is actually a negative shear force, and all that's going to equal 0. And so we can easily solve for V here, which is what we want. We want to know what our shear force is. How does it vary along the x-axis of the beam? And so V will just simply equal W times L over 2 minus x. And you can immediately see that V varies linearly with x along the length of the beam. So that's our first equilibrium equation. The second one we can do would be summing our moments about C, setting that equal to 0. And so for our moments about C, we have this WL over 2, and that's going to be times the distance x. This is going to cause a positive or a clockwise rotation. Sorry, this is going to cause a clockwise rotation, which means it's going to have a negative sign out front. So we negative WL over 2 times x. That's the arm. We're going to have our WX here, and that's occurring at a distance x over 2. That's going to cause a positive counterclockwise rotation, so we'll end up with negative WX times x over 2. And by the way we drew our moment here, we're going to have a positive moment. And so now we can easily solve for our moment as a function of x, which is going to be m equals w over 2 times lx minus x squared. W over 2 times lx minus x squared. So we can immediately deduce a couple of things from these from this free body diagram and our equilibrium equations. Our shear force varies linearly with x. Our moment is quadratic with x. And so what we can do, and what we want to be able to do here, is extract from this information what a shear and bending moment diagram would look like. And that means simply that we're going to plot this equation for shear force and this equation for the bending moment along the x-axis of this structure. So let me redraw it over here. And so a uniformly distributed load W going from A to B, resting on simple supports, is going to lead to a shear force V, which at x equals 0 is going to be equal to WL over 2. So if we plot V as a function of x, we can put a point here, which would be WL over 2. And at point of x equals L, we're going to be at a negative WL over 2. We know this thing is linear with x, and so we'll go through the center of the beam to this point here. And we can just kind of sketch out the areas under these curves here. So we have a linear shear force as a function of x, which starts at WL over 2 and goes to negative WL over 2. We can do the same thing for our bending moment. Here we're going to plot m as a function of x. And this thing is quadratic. And what you find is that it's going to make be a positive x squared, and then that sign's going to flip as this thing crosses through the origin. So one immediate thing to note here, and let me just sketch out this area. This thing crosses the origin here at the midway point of the beam. So the shear force is equal to 0 at L over 2. The shear force goes to 0 there, but if you just simply draw a line here, what you note is that our moment becomes a maximum at the center of this beam here. Again, this is corresponding to L over 2. And so we can simply put in L over 2 for x here to get what our maximum moment is, and it's going to be negative L over 2, negative L squared WL squared over 8. And so what we've done here is introduce the idea of shear moment diagrams. These are ways to be able to visually extract the shear force at any point along the beam as you go from one end to the other. You can also extract the moment at any point along the beam as you go from one end to the other. We got these curves just from a simple statics analysis. We put an arbitrary cut in our beam. We turned this distributed load into a point load acting on this arbitrary element. We got two equilibrium equations, one for summing the forces and one for summing the moments. And this gave us our shear force and our moment, and both of these were functions of x. So this is really v as a function of x, and this is really m as a function of x. And all we've done is simply plot these. And so you'll work through some exercises where you can do this for a variety of different loadings and different boundary conditions. And what we'll end up doing in our next lesson is kind of really exploring this relationship between this curve here and this moment curve. And we'll go about a different way of approaching these same shear and moment diagrams. Instead of using a free body analysis, we can use kind of some differential relations between the load W, the shear force V, and the moment M.